Hello and welcome to the next 2020 Shell Eco Marathon virtual learning session. Today with Altair Engineering. My name is Norman Koch and I'm the Global General Manager of Shell Eco Marathon. First of all, I want to start by thanking all of you for your tremendous flexibility and understanding as we have evolved Shell Eco Marathon due to the impact of COVID-19. And as this situation continues to change, the health and safety of the Shell Eco Marathon participants and our organizing teams remains our top priority. Given the current status, we're really excited that you have joined us here today in this new digital environment to kick off our virtual learning program, all from the safety of your home. And I hope please stay safe during the webcast and look around you and be cognizant of the dangers that might be there. Today, you'll be hearing from Eric Larson from Altair Engineering about creating lightweighted, optimized designs. Altair is a global technology company that provides software and cloud solutions in product development, high-performance computing, and data analytics. Altair has been supporting Shell Eco Marathons by supplying licenses, training, and support for Altair HyperWorks to all our competing teams in the Shell Eco Marathon event. Eric is the Technical Account Manager for Education at Altair Engineering, and he's been working at Altair for over 13 years. He studied mechanical engineering at Michigan Technological University and has 30 years of experience in product design and analysis. So welcome, Eric, and we look forward to hearing more from you in just a few moments. But before we get there, just a couple of housekeeping comments on this webcast. We, of course, would like this webcast to be as interactive as possible. So if you have any questions throughout these presentations, please go on your browser to the website menti.com and enter the code shown on the screen below. On Menti, you'll be able to post your questions, see the questions of others, and give a thumbs up to other questions so that we can answer the most important and most relevant questions first. If by any chance you have any issues accessing Menti, you can also post your questions on the YouTube comments on the right of the live stream once you have logged into YouTube. Eric from Altair will then be answering your questions after the presentation portion of our live stream. And just in case, as this is a live stream, so if for any reasons we run into technical difficulties, please bear with us and be patient as we sort out the problems. That's pretty much all from me now. I'll hand you over to Eric from Altair, who will officially kick off the sessions. Eric, it's over to you.
Awesome. Thank you so much, Norman. And thank you to everyone who's taken the time to join us here today. I know this isn't the Eco Marathon we were all hoping for, but I do want to send my gratitude and appreciation to Shell for pulling this together and giving us something that we can enjoy in these trying times. And just to give you a little bit of information about our background, Altair is now in its 4th year of proud sponsorship with the Shell team in the Eco Marathon. But even before that, we have supported super mileage and pretty much all types of competitive design teams for many years prior to becoming an official sponsor. We support with providing our software to teams, providing support on the software, providing mentoring. And Altair, with its incredible CFD structural and optimization analysis capabilities, is a great fit for any competitive design team, especially those looking to improve vehicle performance in fuel economy and energy efficiency and lightweighting in general. So what I want to do is kind of kick things off here. I'm going to show you a couple of slides. Sure that this presentation is as exciting as possible. So we're going to limit the amount of slides. I've only got about 4 of them here, and the entire rest of the presentation will be a live demonstration of the software. And please keep in mind that this software is available to all teams through our corporate sponsorship, as well as education versions of the software. So Inspire is a package that allows you to very easily, very quickly, and very accurately perform structural analyses on your parts, and perhaps more importantly, provide you a manner of easily coming up with optimized designs. So what is an optimized design? You may have heard these terms: optimization, generative design, all of these catchphrases. Optimization is really something that Altair kicked off 25 years ago. And it's the idea of taking a designed part and making it lighter. And we do that intelligently by determining where important material should be and getting rid of the rest of the material. So this slide provides a very good example of that. This is an original design here. It's a truck support. This picture does not do it justice. This part is absolutely huge, and it weighs a tremendous amount. And this is a cast part here. And back when we were perhaps less concerned with fuel economy and energy efficiency, this part was fine, and it was a beast. It would support loads with no problem. But as we move into a more greener environment, as we're looking to get more fuel efficiency, more energy efficiency, and a smaller carbon footprint, we want to make sure that we don't over-design parts. Not what we have here, an over-design part. So using the Inspire software, what we can do is we can take this original design and very quickly, very easily come up with an optimized design. And this is an example of what Inspire is going to provide us. You see, it's removed portions of this material. It's determined where material is necessary and got rid of the rest of that material. And then from that, we can then come and engineer our own design from that, taking cues, taking information from the optimized design, come up with an engineered design right here that is an incredible 55% reduction in mass. Another added advantage of using a simulation-driven design process is to take a conventional design process, which is to come up with a design, test it, either virtually or physically test it, and then determine where it can be improved, and ultimately come up with a new design that we're going to test again. And this can be a long process. You can see here their original aircraft door hinge bracket weighed 9.15 kilograms and took 3 months to design. Using our optimization simulation-driven design with Inspire, not only were they able to see a significant reduction in mass, which in aviation is critically important, but more importantly, was able to drop that design time from 3 months down to a mere 3 weeks. Another critical aspect of design is design for manufacturability. The best, most incredibly designed part ever is completely useless to us if we can't manufacture it. And Inspire does have built-in manufacturing constraints that allow us to specify the way that we're going to manufacture the part. And in this case, this VW part, this was the original design. We were able to see a significant weight savings, but most importantly, we were able to come up with a design that can be manufactured using the casting process they intended. Lastly here, and the final and one of the other most important aspects of a simulation-driven design is making sure that not only do we reduce parts or reduce weight and make it manufacturable, but it has to adhere to the design requirements that we specify. Strength, stiffness, and in this case, this is an antenna bracket that is currently orbiting the Earth on a satellite. This was the original design, this kind of boxy thing here. You can see the original weight was 1.626 kilograms. Using our optimization-driven design, we were able to reduce that down to less than a kilogram, a 42% weight reduction. But most importantly, in this case, all the design criteria were satisfied. And in the case of a part launched in space, it's going to experience a tremendous amount of force, a tremendous amount of stress initially, and we want to make sure that the part survives that very violent launch into space, because once it's up there, there's no fixing it. And I'm happy to announce that this part did survive and is currently supporting the antenna and broadcasting the information from this satellite. So, as I promised, this is all I'm going to do from a slide standpoint. The rest of this is going to be a live demonstration of the software. So I'm going to open up the software here, and we're going to move on and do all of the things that are necessary to achieve these goals, to achieve these. Yes, I'm sorry? Okay. So we're going to go through the software and achieve these designs, achieve these analyses using the software. So This is Altair Inspire here. You can see it's very, very easy to use software. It's very simplistic in its structure. Along here on the top, we have our pull downs, the locations where we can specify what we want to do with it with Inspire. The first one here, geometry, is where we're going to have all of our geometry functionality. Then structure is where we're going to set up our designs and our analyses. Motion is where we can do motion capabilities, and then manufacture is where we can specify our manufacturing requirements or analyze manufacturing capabilities. We're going to talk primarily about geometry and the structure. We'll discuss motion briefly. But to give you kind of an insight into how to get around the software, let me turn these off first of all, because this is going to be the window that you're going to see when you first install the software. What I like to do first of all is to come up here to the View pull down, come to the Model Browser, come to Property Editor, and turn these windows on here. What these windows are going to do is allow us to see information about our part when we bring that up. You'll see you can also turn them on using the F2 and the F3 keys. You're going to lose a little bit of the graphic window here, but it's worth the information that you're going to achieve. Some other aspects of this, pretty much most everything within Inspire is clickable. So this, I can alter my views here. We can turn parts on and off, save views. But really, to understand how to go about doing this, it's best to have a part in here. So I'm going to come here and I'm going to come to File and Open. And you'll see here that Inspire does support all of the different CAD packages that are out there in their native formats, as well as a third-party format like STL, Parasolid, Step, or IGES. The part that I'm going to bring up here is a Parasolid file, and so I can select that. I can click Open, and once we open that up, we're going to have that geometry here within Inspire, and we can begin working on it. Before I get going on it, let me just remind everybody again that if you do want to post questions, I will be getting to a question and answer session at the end of this. Please go to menti.com and enter the code 562036, and you'll be able to post questions in there that will be related to me at the end of the presentation. So I've got my geometry here, and with this geometry, what I can do is come here and begin to set this up for an analysis. And to do that, the first thing that I want to do is make sure that this part is made out of the correct material. You can see it says 9.4041 pounds here. What I want to do first of all is I want to change the units that that's in. Changing the units is very, very easy. All I have to do is come here to the corner, and in the corner here, I get a list of all of the common unit schemes. I'm going to move over to a millimeter Newton second unit scheme, and you can see it updates that. Because I'm working in millimeters and newtons, the mass is then going to be calculated in metric tons. But you can see if I instead switch to a millimeter Newton kilogram scheme, now it reports that in kilograms. Units are very, very easy within Inspire. All I have to do is switch the scheme to whatever I want it to be, and the part will automatically update to that new unit scheme. All of the dimensions on the part will automatically change. Any loads, anything that I've put on here will automatically update to whatever unit scheme I'm in. So I'll leave it in millimeter Newton seconds right here. That way I know that my results are going to be in megapascals, and I can always quickly convert back over to kilograms just to get an idea of the weight, the mass here. So you can see we're at 4.2656 kilograms. The part is automatically assigned a material when it's loaded in, and that default material is a steel AISI 304. But the first thing that I want to do is make sure that I assign this a material appropriate to my design. So if I right-click on this, you'll see I get a list. If I come to material, I get a list of all the materials here. Everything from steel, ASI 304, the default material, down through plastic, nylon, and ABS, which are useful for 3D printed parts. This is all comes with the software. It's a library of materials that comes with the software, and I can select from any of those. In fact, I'm going to select aluminum 7075 T6. And you see, as soon as I do that, if I switch back to kilograms real quick, you see we've had a tremendous weight reduction already just by making this out of aluminum. But oftentimes, we're going to want to use a material that's maybe not on that list of materials. Especially if you have the specifications for the material you want to use, all we have to do is come to the structure ribbon here, come to this materials option. It's going to list all of the parts in my model and the material associated with it. But in this case, what I want to do is come over here to my materials, and you'll see I have two of them put in here. Douglas fir. I was doing some work with some wood, and then just one that says Eric's material. All I have to do is click plus. It's going to add a material to this, and then I just need to enter in the values here. The E, the Young's modulus, the nu, the Poisson's ratio, the density of the material, the yield stress, and if I'm planning on doing a thermal analysis on this, the coefficient of thermal expansion. And as I switch from unit to unit, you'll see that those will adapt to whatever unit scheme I'm in. So we'll leave it in MPa. And I would just put in the material specifications there. As soon as I do that, in the right click here, you'll see that new material is available in this library. So we can add as many of our own custom materials as we want. But as I said, I'm going to leave it on aluminum 7075 T6. So ultimately, I'm going to want to optimize this part. I'm going to want to create a design that is as lightweight and efficient as possible, but able to support the loads that I put on it. To make sure that I am working intelligently, the first thing I want to do, though, is I want to run a quick baseline analysis. It's always important to know where we are now, so that when we go to the optimization and we get an optimized part, we want to make sure it at least meets the specifications that I've got right now. To do that, I'm going to need to set this up to be a linear static analysis. Linear meaning we're dealing with material in the linear range, and static meaning the part is going to be held in place, fully constrained, but allowed to deform locally. And we'll get setting up with that, but one of the first things that you're going to want to know as you begin to utilize Inspire is how to manipulate the part. And the default mouse manipulation within Inspire is holding down the middle mouse button allows me to rotate the part. You'll see that little X there is what I'm rotating around. If I want to pan the part, I hold down the right mouse button and move it back and forth, up and down. I can pan that. And if I want to zoom the part, I just roll my scroll wheel. As I pull my scroll wheel toward me, it's zooming in, using the pointer as a focus, or push my scroll wheel away and it zooms out. But one of the most difficult things, or one of the most inconvenient things about moving from software to software, especially GUI-based CAD-type softwares, is every single software seems to have its own unique mouse manipulation. We wanted to get away from that. We wanted to make sure that a transition from another software into ours, from a CAD software like SolidWorks or CATIA or UG, Pro-E, into Inspire was as seamless as possible. If you come to the File pull down here, and you come to Preferences, and then you select Mouse Controls, you'll see that the default mouse control is what I explained here, and I can click on those and change those to whatever I want. But if I click that word default, it's going to bring up a list of very common CAD packages. SolidWorks, I know, is a very popular one amongst students. If I select that, you'll see it's going to change, and it's going to say now default settings for SolidWorks. So whatever the pan, zoom, and rotate mouse manipulations are in SolidWorks, Now that's going to be the way that we do it in Inspire, which means moving from SolidWorks into Inspire becomes as seamless as possible. Now I don't use a CAD software, so I just stick to the default within Inspire. So I'm just going to select that, but hopefully this will make things a little bit easier, a little smoother, and a little more comfortable for you as you transition your geometry from your CAD package into the analysis tool like Inspire. So with that said, the very first thing I need to do now to actually run this analysis is I need to indicate how the part's going to be held in place. I did say it was a static analysis. So for it to be a static analysis, we need to make sure that the part is fully constrained somehow. And I'm going to make sure I'm in my structure ribbon here. And when I'm in my structure ribbon, I just come over to the loads icon. And you'll see when I'm in the loads icon, or many of the icons within Inspire, these icons are not just push a button and then open up another menu and then push a button and open up another menu. All of the functionality is right here on top of this icon, because what we were able to do was introduce the idea of what we call multi-function icons. What a multi-function icon does is it takes very similar tools, very similar functions, and combines them all into one icon. So this is not just a button to push, but actually a collection of buttons that form this image. And we made it a very large, very descriptive image here. So if I want to create my supports, you can see I've got these little cones supporting my part. If I move on to that, they turn yellow or get a yellow halo around them, and that means I'm creating supports. If I come up here to this force vector here, I'm applying a force. So if I come to this like porcupine looking thing here, I get to apply a pressure or a moment here. So all of the different possible forces or supports that I can apply to a part are on this one icon, allowing for a nice large icon and a very organized way of doing things. The first thing I want to do is create my supports. The supports will be what are going to hold this in place. And once I select that, I get this little modifier on my pointer, the little cone on my pointer. Lets me know I am creating supports. And it tells me that I can apply that support to a point, an edge, a face, or a hole. And for a point, edge, or face, all I have to do is hover over that. That's going to highlight. And when I select that, it's going to put an icon there. This is my little support icon. It will put it wherever I clicked on there, but the most important thing is that this entire face shows up as red, so that entire face is being held onto by that support icon. And now that face is as if it's welded or glued or stuck somehow to something else. That face cannot move. But many times we do need our faces, points, lines to move in a certain direction. So maybe this just prevents it from going up and down. If I double click on this, I get these little arrows here. Right now, since all of the arrows are faded, the part is fully constrained. But if I select any of these arrows, that arrow turns green. And now if I right click to get out of the function, I get these little roller wheels indicating the direction that this is now allowed to move. So I have freed it up in the direction, which happens to be the Y axis there. I've freed it up to move in that direction. So it can't move up and down in the Z, it can't move forward and backward in the X, but it can move in the Y direction. And if I need to free it up in a direction that isn't aligned with one of the cardinal axes, again, it's very easy. All I have to do is double click on that, and I come to this little universal moves tool here, and it allows me to rotate that about any of the axes, either in 5-degree increments or coming in here and typing in whatever amount I want, and it will align to that. And you can see now the roller wheels are pointing into that direction, 37 degrees off of the Y-axis. If I select the other in-plane arrow, you see now I get this little caster wheel on here, and that now tells me that it's free to move in plane, but it can't move out of plane. So I can create very unique, very custom, very complex constraining supporting schemes by manipulating those arrows right there. Now, of course, I don't want to constrain that in that direction. What I'm going to do is I'm going to constrain it down here in these bolt holes. So when I'm in support, it did say I could do a point, an edge, a face, and those act the same, or a hole. And in this case, these holes are where this part is going to be mounted onto the aircraft. This is, as I mentioned, an aircraft door hinge bracket. The way this works is if I take two of these and I kind of put them into that orientation right there, and I can get them exact orientation I want by clicking the Z-axis. So if I orient them like that, you can imagine that there's one up here, one down here. These are on the door. And then if I flip that around, we'll do it. This will do it manually because it's going to make it upside down if I flip it that way. If I flip that around, one here is going to mount on the frame of the aircraft. And actually that door hinge that we saw in that previous slide is going to mount between them. And that's going to allow that unique action of the door opening and closing on an aircraft. So to make sure that I model this in the way that it's going to be mounted into the aircraft, what I want to do is I want to hold on to these 6 bolt holes here, and I'm going to do that by applying my constraint, my support, to a hole. And when I click these holes right here, I get a slightly different icon than I was getting before. This icon is unique because Inspire is recognizing that this is a hole, and it's recognizing the fact that there are typically unique properties to a hole constraint, and that is, when it comes to a hole constraint, the majority of the time we're either pinning that hole, so holding it in place with a pin, potentially a clipped pin, or we're bolting in that location. So the constraint looks a little bit different, and if I double click on it, I get slightly different freedoms. The first of which is the rotation. So I can allow it, if I free that up, I can allow it to rotate about the axis. So as if I've pinned it, but it's a clipped pin right now because it's not free to move along the axis. I can free it to move along the axis by selecting that. And those are the two freedoms that I can apply to a hole constraint, moving along the axis, rotating about it, either one or none. But no matter what, it will always be constrained normal to the axis, indicating that it's pinned or bolted in place. I'm going to leave these just as is. And now what I've done is I've simulated bolting this in to the aircraft. And it is now rigidly affixed in those locations, but the rest of the part is free to deform. So that's important for a static analysis, that the part is rigidly held in place, but the rest of the part is free to deform. And what's going to cause that deformation are the loads that we apply to this. So I'm going to come here to my loads, come back to my loads icon, and like I mentioned, I can do a force that's going to be put onto a point, a face, surface, or a hole. I can do a pressure or a moment. I'm going to select the point force, and again, it says point, edge, face, or hole. And if I select a face, it will put that load icon wherever I indicated. But again, just like the constraint, because that entire face turns red, that means that that force, this 1 Newton force, is applied across and evenly distributed across that entire face. But what I want to do, so let me select that. I'm just going to click my delete key to get rid of it. I want to apply it to the hole. So I mentioned that the aircraft door hinge attaches to these holes here. So I'm going to put my force in the hole. It will put it at the center of the hole, but it will highlight that entire surface in red, indicating that the entire surface is, that load is being applied to the entire surface. And I can select the direction I want that to go by selecting any of the cardinal axes, so X, Y, or Z, plus or minus to move it back and forth. Or just like I did with the constraint, I can take that, get it generally aligned, and come to my move force, and then I can rotate that in any of the axes that I want to orient it in the direction that I want. And I would do that if I had my orientations via angles, or if I knew the angles off of the cardinal axes. Another way that I could do that, excuse me, is to use this little icon here, this little down arrow. And when I select that, you're going to see the values, the portions of a unit vector. So if I know my vector components, I can come here and put them in. So say I know 3, 4, 5. I'm going to align that using these as a vector for the orientation, but not touch the magnitude. Or if I switch this from a direction force mode, or from a direction mode to a force mode, now these become not only components of the direction, but components of the magnitude as well. So as I change these, 3, 4, 5, it will not only change the orientation, but it will change the magnitude. So whatever information I have, I can orient this in the way that I want. What I'm going to do is I'm just going to orient this in the y-axis, the negative y-axis, and I'm going to put a value in here. So we'll say 2,000 newtons. Now this part is going to see multiple load cases. When this is mounted in place, this is going to represent a situation where the door hinge, or the door is closed or is open, and the door hinge is pulling down on this. But we're going to have another scenario where I'm pointed in this direction, and the arrow is going to be representing the force when the door is closed and that hinge is pulling on it. And I can now, I've oriented it the way that I want. I can now again put in the value that I want. But let's say, for instance, you didn't happen to know what the force was in newtons. Somebody had given it to you in pounds force. So I could go and I could do the calculation. Go to Google and Google what is 500 pounds force in newtons. I could come down here and switch to pounds force, put 500 in, switch back to millimeters, Newton seconds, and have it convert. Or if I come in here and just type in 500, if I clicked enter, it would be 500 newtons. But if I type in LBF for pounds force, you see it automatically converts that to newtons for me, or whatever my current load is. So we do truly try to make units as seamless as possible within Inspire. So now I've got my forces, I've got my constraints, I've properly assigned a material to this. The last thing that I need to do is I need to differentiate between these two forces here. Right now, these are going to act together. So they're going to act at the same time, which of course is impossible. This door cannot be open and closed at the same time. But I do want to understand the behavior of this, and then ultimately when I optimize this, I want to make sure that it is taking the information from all of these, or from both of these different load cases. I want to come here and I'm going to come back to my load icon, and I'm going to select this right here, and I can add another subcase to this, another load case. And what that means is both of these will be analyzed, but they'll be treated as two separate events. So I will get two answers from the analysis. And all I have to do is, kind of buffet style, pick what I want for the supports, and then pick the force that I want, turn this force off, and now I have two entirely independent load scenarios, using all of the supports and force 2, and using all of the supports and force 3. I could even come in here and say, model a scenario where I'm going to assume that 2 of the supports have broken, 2 of the bolts have broken, so I will not select support 2 and support 3. I'll just select these right here, and we'll say force 3, and I can continue to add different scenarios as I want. So now I have 3 different load cases, 3 different studies that I want to run. And please remember, as I go through this, make sure if you have any questions, you log on to menti.com and enter that code 562036. I see that showing up at the bottom of the screen. So make sure you go to Menti, enter that code, and you'll be able to ask any questions. Ask them now while they're at the top of your head. And I do promise we'll get to as many as we can at the end of the session here. So now I've got it all set up. I'm ready to go. But before we run it, I just want to talk about some of the other options that we have here. I can apply what we call enforced displacements. So say I didn't know the load that was going to be, but somebody went and loaded this up and measured it, and they measured that this point moved 4 millimeters. I could come to an enforced displacement, enforce a displacement on that point, say 4 millimeters, in whatever direction. That's the wrong, so I'll click minus and move it down. You can see it's now indicated that that point is going to move 4 millimeters. So what's going to happen is it's not going to load it. It's going to take and forcibly move that point 4 millimeters, and then I'll be able to find out what stresses incur or happen as a result of that enforced displacement. So another way that I can load this part up. I can do G-loading. So I can click on a part and G-load it, or I can do angular velocities or accelerations. We'll come back to gravity when I come to run it. And I can do temperature loading. So if I select that and pick my part, you see it indicates a delta T. So I could say 150 degrees Kelvin delta T. So it's an increase of 150 degrees Kelvin, irrelevant of what it started at. It's just a thermal load. So we're going to get expansion if the heat goes up, and contraction if the heat goes down. So I can do a thermal load as well, but let's delete that. So those are the different loading scenarios that I can do. Everything is set up and ready to go. The last thing I need to do is just go and run it. So the way that I'm going to do that is I'm going to move all the way down here to the end of my my list, and we have our analyze. If I click this little run OptiStruct analysis, if I click this, it's going to open up this little window here where I can name my analysis. And if I'm going to be running multiple analyses, I always find it very useful to change the name. Right now, the name is just going to be whatever the part name is. Excuse me. But what I can do is change that, and that's help me differentiate between the different analyses, the different studies that I do. You'll notice I haven't mentioned elements up till now. And if you're familiar with the concept of finite element analysis, you know that all of these analyses are element based. As a little teaser for tomorrow's session, which is going to deal with SimSolid. SimSolid is actually a geometry-based analysis tool. So stop on by for that one if you're interested in seeing an incredibly quick analysis that doesn't even use elements. But this is an element-based analysis, so it has automatically calculated an element size, a global element size. I can change that if I want, but I'll leave that alone. I can incorporate a normal modes analysis into this. By doing a normal modes analysis, I will get the modal frequencies. So if I select that, it defaults to number of modes of 10. So I will get 10 normal modes, and then I can either do it as an unsupported, a free analysis, or I can use the supports from any of my load cases. So load case 1 and 2 would be the same because they use all 6 supports. Load case 3 would be slightly different because support 2 and 3 were not utilized. I'll do it as an unsupported. I can do buckling modes. So if you're interested in buckling, I can get my buckling modes. Speed versus accuracy. I'm going to leave it at more accurate. I do want accurate results, so I want to make sure that they're as accurate as possible. I always recommend doing it more accurate. The only time you ever want to do faster is if you find that your analysis is taking an inordinate amount of time and you just want some rough results real quickly. The results will be good, but they're not going to be as accurate as possible. If you're interested in the details behind it, more accurate is going to use second order quadratic elements, and faster is going to use first-order linear elements. Contacts, we'll get to that in a bit, so I'm just going to leave that as is. Gravity, do I want to incorporate gravity into this analysis? Right now it's set for no, and that is the default. And what that means is it's just going to assume no gravitational effects. And on this part, that's perfectly fine. The part is relatively compact. It's not going to experience gravitational effects of any discernible amount. If it was maybe something really cantilevered, I'd turn that on, and then I'd need to come here to gravity and make sure gravity is pointing in the correct direction. Right now it's not. In this case, gravity would be pointing in the negative y-axis. And then the gravitational acceleration is set for Earth standard. Maybe someday we'll have Shell Eco Marathon Lunar competition, in which case we'd want to change this gravitational acceleration. But for the foreseeable future, we're doing this on good old Earth. So we'll leave it default for what it is. If you do need to do a G-load, don't mess with this. It's better to actually do a G-load up here where I can specify a specific G-load and just leave the gravitational acceleration alone. But as I mentioned, there are no gravitational effects on this, or no discernible ones, so I'm going to leave that off. The final option here, load cases. Which ones do I want to analyze? I want to say all of them, and all I have to do is click run here, and we'll run the analysis. And what it's going to do is it's going to go through and set this up for an analysis. Now, the power of Inspire is the fact that while this is incredibly easy to use, incredibly quick to set up an analysis, it's utilizing in the background our enterprise level tools. What it was doing was first it sent it off to our batch meshing, our auto tetrameshing tool, SimLab. SimSolid is what we're going to discuss tomorrow. SimLab is our tetrameshing, auto meshing tool to create a very high quality tetramesh. Once it was done with that, it sends it to our pre-processing tool, HyperMesh, where it's going to actually take that mesh and then set up all the parameters for analysis, or as we ultimately get to it, optimization. And now when it's about 2/3 of the way across here, it's now sent it to OptiStruct, our high-end, very, very accurate analysis and optimization solver, and it's running that quick solution right now. That should be done relatively quickly. It is going to take just a couple of minutes here, where it will some result. While it's going through this, I do want to mention that if you're using the latest version of Inspire, 2019.4, and you can get that through a corporate sponsorship, we actually do have the ability to come up here to File and Preferences, and under Run Options, we can change that analysis solver from OptiStruct to SimSolid, the tool that we're going to talk about tomorrow. So the tool that we'll talk about tomorrow, SimSolid, is the full software where we're going to do all of our pre-processing in there. What this will do is we'll switch over to the SimSolid solver. The reason I'm not going to do that is because SimSolid is limited to analysis only. We can't do optimization in it. And my ultimate goal is to take this and do an optimization. But had I selected SimSolid as my analysis solver, this would have been done almost instantaneously. From the time I click the run button to the time I get results is a matter of probably 10 to 15 seconds or less. And you'll see that in all of its full glory tomorrow when we actually use the SimSolid software. But because I am taking this from an analysis to an optimization, I do need to leave it in OptiStruct so that we can utilize the incredible optimization capabilities of OptiStruct. And fortunately, in the time that I discussed that, it has completed. We get our little check mark here. We get our little green flag letting us know that we've solved, we've come up with a solution. I click that green flag, it will automatically take me into post-processing mode. And in post-processing mode, I can view all of the different result types that I have: displacement, factor of safety, percent yield, and my stresses. And I can change that between the different load cases. Additionally, I can animate it. So if I click the animation, It's going to show me, based upon load case 1, what the animation, the deformation of this is. It is an exaggerated deformation. This is not how much this part is moving. We exaggerate it because we want to see the behavior of it. If I come here and I see that this is actually 376.5 times scale, if I turn that off and select 1 time scale, you can't even see what the deformation is until you really zoom in very far. Not very useful to me. I need to understand the behavior of this, not necessarily the exact amount of deformation. That I can get from my chart up here, my legend. These numbers are correct, but the animation is exaggerated so we can understand the behavior. I can come down and take a look at my stress. When I look at my stress, I can see the stress on this. And then I can come and select my different load cases as well. So load case 1, load case 2, and then load case 3, which, as you can see here, is incorporating those broken bolts, so the part is moving from that. I can also view factor of safety. And let me come back to my load. Okay, factor of safety, it's going to take into account the yield stress that you put into the material definition. And it's going to tell you how much of a times factor of safety I have with the forces that I put on there. And this is important for this part because you're going to see that I'm in the blue here, which means I am a minimum of 6 times factor of safety for the entire part, and I can isolate that by moving this down. What this is going to do is it provides a cutoff. Not very useful here because everything is above 6 times. Just to show you how that works, if I come back to von Mises stress, the cutoff allows me to isolate things by their value. So I can see the highest stresses here. And the highest stresses in this case are relatively low. In fact, like I said, I'm seeing a 6 times factor of safety on this part. That's great. The part is very well designed. From a factor of safety standpoint, this is an incredibly designed part. The problem is it's over-designed. Way over-designed. There is no need for a 6 times factor of safety. In a lot of cases, especially with like an eco-marathon vehicle, if you have your parts designed with that high of a factor of safety, you are lugging around way too much material, and you're not getting that that super mileage that you're looking to get. So while we always want to incorporate some degree of factor of safety, we want to keep it a reasonable amount that's going to guarantee we are going to be designing to the type of stresses, to the type of scenarios that we expect to see with a little bit of extra safety built in there. So the reason why I did this is to find this information out, find out how much room I have to improve this, and at 6 times factor of safety, I have a ton of room, which is going to lead real nicely into my next section of the presentation, which is optimization. But before I do that, let me just remind you again, if you have any questions as they come up, make sure you go to menti.com, and that code is right there at the bottom of your screen, 562036. Enter that in, and I really look forward to getting your questions and answering them at the end of the presentation. We are allotting a significant amount of time to make sure we get to get all of your questions. So no matter what question you have, I've long and always said that the only dumb question is the question that's not asked. So please ask your questions. I'd love to talk about them at the end of this session. Okay, so I've got my part here, and it is way over designed. We know that, and I want to make sure that that I create an optimized part that is as efficient and lightweight, and not only lightweight but as strong as possible with the best material utilization. So I'm going to move into optimization here. Before I do that, I do want to mention one thing. This is a simple design. This is one single part here. But many times we have multiple parts that come together. So what I'm going to do is I'm going to open up this part right here, you probably recognize this as a drone body. I'm not going to do any analysis on this, but I'm going to utilize this part because, as you can see here, there are a large number of parts that make up this design. Even these arms here are broken into separate solid parts. When we bring that geometry in from CAD, it will maintain that design structure, maintain that organization, and maintain those part names. But when we have multiple parts that come together, we want to make sure that we have one contiguous model. And Inspire does that automatically for you through the use of contacts. And on the structure page, if I come here to the contacts, you'll see that all of these blue surfaces are what we call bonded contacts. Imagine you took those two solids, you put an infinitely strong crazy glue on them, super glue, stuck them together, and now they are permanently bonded together. That's going to make sure that this part acts as one piece. But in the case of this part, not only do I want it bonded together at these arms, I want an accurate representation of my design intent. And that's not what I'm going to get if it's bonded at the bottom and the top here, because the bonding is not what is holding this together. It's actually these bolts, these screws. And so by bonding it at the top and the bottom, I'm going to get a slightly unrealistic behavior. It will run, I'll get very, very close results, but it's not going to be perfect, or it's not going to be as accurate as possible because these parts truly aren't bonded together. They're held by the bolts. So what I can do is, in a combination of the automatic bonding, I'm actually going to remove these geometric representations of the bolts. So I'm just going to do a shift select and click my delete key. Those are going to go away. My contacts are still there. It's bonded, but the bolts are gone. But now if I come here to fasteners, it's going to automatically find concentric holes that run through the part, run through multiple parts, or a hole that runs through one part or multiple parts and then doesn't completely run through the last part. For these through holes, it's going to put bolts in. For these blind holes, it's going to put screws in. When I click fasten all, it will put representations of them. And most importantly, what it then does is any surface that's affected by that bolting process, it's going to turn that from bonded to what we call contacting. So now these surfaces are free to slide along each other. So they're not bonded together, and that's going to force the force through the retaining bolt and not from bonding on these. And then when I come to analyze, if I change this from sliding only, which allows them to slide across each other, imagine two very, very strong neodymium magnets. You put oil between them, you squeeze them together, they can move like this, but can't pull apart. That's what we get with our standard sliding. If I do sliding with separation, that will allow these to separate if it detects that it's necessary. It will add some time to the analysis because it's constantly analyzing that separation, but we'll get a very, very accurate result on that. But realize, had I not done that, it still would run perfectly fine. All the parts would be connected together. Any solids that touch will be automatically bonded together. But to get a slightly more accurate result, we were able to adjust that bonding by adding in our bolts here. Okay, so what I'm going to do now is come back to my design here. And I want to optimize this. I want to find out the perfect design for this. I want to make sure that I'm utilizing just the material that I need and nothing more. So I want to optimize this part. Now, optimization, if you're not familiar with it, and it comes with a number of names, we call it optimization because that's what it truly is. I know that kind of the key phrase or the catchphrase these days is generative design. Generative design is just another name for optimization. We started the optimization process and the optimization craze 20 some odd years ago with our OptiStruct. And now there are a number of softwares out there that are kind of copying what we do, and they're doing an okay job at it. But the true optimization generative design capabilities are what you're going to find in our OptiStruct software. But what optimization, in this case, or generative design, whatever you want to call it, what it is its true name is topological optimization. And topological optimization is very similar to sculpting. So imagine you want to carve a sculpture. You're going to take a large block of material and you're going to carve away what you don't need. What people don't think about is when you're sculpting something, you're actually not creating a sculpture. You're simply taking the excess material that surrounds the sculpture that's in there and removing it. Well, that's what topological optimization is. I give it a large block of material and it carves away the unnecessary material. But just like if I'm going to do a artistic sculpture, I want to give it the largest block of material possible. I want to do the same thing if I'm doing this topological optimization sculpting. I don't want to optimize the part that already exists. I don't want to utilize their light weighting features. I want to give it a nice block of material that it can carve from. And so I'm going to come back here to my geometry tab. And within Inspire, you could do this in your CAD package. This absolutely could be done in the CAD package. But there are some tools within Inspire that are actually easier to use than the CAD package. So create your initial geometry there, and then if you need to do any manipulation, do it in Inspire. If I come here to simplify and holes, what holes does is it detects holes in my part and I can fill them up. It didn't detect these, so all I have to do is double click in them. Click it one more time and it fills that right in there. And you see what I'm doing is I'm removing those light weighting features that were put in here so I can get that nice big block of material to carve my part from. Next thing I want to do is I'm going to come here and I'm going to select my push-pull. So I'm going to grab this and I'm going to pull this out. So again, removing these light weighting features that were put in here. And now I've got this nice big block of material necessary for my optimization. This is an ideal part. Now we've added a lot of weight to this, obviously, by bulking it up, but that's fine because what we're looking to do is provide that base block of material that the optimization code can remove from. But we're not quite there yet. One other very, very important aspect of this is the fact that there are aspects of this design that are critical to remain, that I can't touch. And what we do with those is we call them non-design space. These are regions, these are sections of geometry that can't be touched. And this hole, for instance, is one of them. I need a perfect cylinder here to mount to that door hinge. In the case of my bolt holes, I need a perfect cylinder for my bolt to go through and hold this in place. If the solver starts carving away at that, I lose those perfect cylinders and suddenly my part is non-functional. So I need to protect them, and I'm going to protect them through a use of a tool called partition. If I click on any geometry when I'm in partition, it partitions that out. I tell it how thick I want that partition to be. We'll say 5 millimeters. And when I right click to get out of there, I now have a separate part here, which means I can right click on this main part here, select design space. And what it will do is it will set this as the design space, the material that I can carve from, but not touch this material here. The next thing I need to do is protect these holes. So I'm going to come back to my partition tool. One of the problems that I have is if I select it as is, it's actually going to protect this entire block here. I don't need that. I don't need the entire block protected. What I need to do is just make sure there's no material here so I can get a tool in here, and that's already taken care of by having that cutout there. I just need to protect the bolt holes. So by holding my control key down and selecting these bottom faces, I can select those bolt holes there, rotate my part around. Again, click my control key, remove those bottom faces so it isolates my bolt holes. Bring that around again, remove these, and protect those. And now you can see I've got all of my critical parts protected, and the rest of my part is set to optimize however the solver feels is necessary. So this entire red portion can be carved away, just like a block of marble when I'm creating a sculpture. But these gray areas they can't be touched. They have to remain. So that's the basic, the initial setup for an optimization. We still have a little ways to go, but it's as easy as that to take our current design and convert it into a good design, non-design space shape. But now I need to come back here to my structure because now I need to define some other parameters for the optimization. Now I said that we can specify some constraints on this, not the types of constraints that hold it in place, but optimization constraints. And those I will find in this shape controls function here. I have, with this red kind of square thing here, I get what we call symmetric constraints. What symmetric constraints do is they guarantee that the part is symmetrical about whatever plane I specify. So if I click my part, it's going to put 3 planes of symmetry on there. 2 of them I don't want. I don't want it to try to be symmetrical about that, and I don't want it to try to be symmetrical about that, but I do want to make sure that my part is symmetrical about the midplane, and what that does is it allows me to take this part and make it universal. So no matter which orientation I want, either mounting this way or mounting this way, I can use the same part for all of the different door hinge brackets on my aircraft because it will be symmetrical about that plane. So we'll guarantee that it's strong in both directions. The next option I have here, this little blue square with the little arrows on it, what this is our manufacturing constraints. Now I'm not going to apply a manufacturing constraint to this, but what the manufacturing constraints do is they guarantee that my part is able to be created in the manner that I look to manufacture it. And the main types of manufacturing we have are single draw, split draw, extrusion, and then we'll come to overhang in a little bit. But from a standard traditional manufacturing, we've got drawing and extruding. Drawing is, imagine it's a cast part. So you have a negative volume cavity, you pour some sort of liquid material in it, you allow that to cool, and then you need the part to come out of that cast. To do that, it needs to make sure, kind of like we see here, that we have angles that go in the direction of the draw, and we have no overhangs or undercuts that would prevent that from coming out of the part, out of the die. That's a single draw. A split draw works the same way, but imagine 2 parts coming together, one coming from the bottom, one coming from the top. And it allows parts that do come out at the wrong angle, but as long as they meet at the parting plane, the part will work. Extrusion guarantees that we have a constant cross-section all the way through the part. The vast majority of extrusion constraint analyses are when we're looking to do a laser cut or a water jet cut on our part. And then finally, overhang. This is a relatively new manufacturing constraint. It was added to account for the overhang limitations of additive manufacturing. So since additive is a layer by layer, or some types of additive are layer by layer, we need to make sure that the layers don't go out at an angle greater than some specified amount, or else we're going to need to either put supports on it or have the potential for a failing part, or a part that fails to be 3D printed properly. So we can specify an overhang angle. With this part, I'm not going to put any restrictions on it whatsoever. I want to make sure that my part is as free to be designed as possible. So I'm going to leave all manufacturing constraints off. And I'm going to go there. Now, when I reloaded my part, I lost all of my my loads, so I need to come and I need to put those loads back on there. But I'm going to skip that because I'm actually not going to run the analysis for you. The analysis happens relatively quickly. It usually takes about 5 to 7 minutes to run this analysis. Sometimes it can go longer. But it's 5 to 7 minutes we really don't have. It's 5 to 7 minutes that's best spent going through some other things. So I'm just going to bring up the end results. But what I would do at this stage is actually put those loads and those constraints back in there. Make sure that my material is set for what I want it to be, the aluminum 7075 T6. And then I would come here to my optimize. When I come to optimize, I now get this menu here, which allows me to specify the parameters of the optimization. And there are some things that we need to set, some values that we need to set to make sure that our optimization is run in the way that we want it. And there are two main things that we need to specify when we set up an optimization. First of all, an objective. What are we looking to do? What is our ultimate goal here? And in the case of this part, we either are going to use maximize stiffness or minimize mass. What is our ultimate goal? In the case of maximize stiffness, so what it's going to do is it's going to optimize this part to make sure that the part is as stiff as possible. But just setting an objective isn't enough, because what it's going to do is, if my goal here is to maximize the stiffness, it's going to analyze this and it's going to say, yep, your part's as stiff as possible. So I need to provide some sort of limitation to it, some sort of constraint. And in this case, the constraint is a mass target. I'm going to say, make the part as stiff as possible, but you only get 30% of the material to do that. It will remove 70% of this big block of material, and the remaining 30% will be as stiff as possible. And 30% is a good place to start. It may not be the end. It may be that you're going to want to adjust that once you see the results, but it's a good place to start. Now, the other option I have is to minimize mass. So you see, minimize mass, now I'm no longer telling it how much material to remove, because I'm saying, okay, now my goal is to get rid of as much material as possible. But again, without any constraint, what it's going to do is it's going to say, okay, get rid of all of the design space, and there you minimize the mass. So I need to give it some sort of limiting constraint. In this case, it's a stress safety factor. It will take the yield stress of the material, and it will divide that by my safety factor and say, okay, this is as high as the stress can go. And as it begins to remove mass for the minimize mass objective, it will limit the amount of material and the location of the material as that stress begins to climb. I can also apply frequency constraints, setting a minimum frequency, or if I'm doing my maximize stiffness, I can set a maximize frequency. So tell it, I don't know what it's going to be, but at least make them as maximum as possible. Thickness constraints are how thin any individual member can be as I carve things away, and everything else is the same as in the analysis. So once I set my parameters, in this case, it's going to be a minimize mass with a stress safety factor of 1.5, and I click run. So just like I mentioned earlier, this would take about 5 to 7 minutes, but we don't want to utilize that valuable time watching an analysis go, so I'm going to load up the results. But before I do that, let me remind you again, if you do have any questions as we're going through this, please proceed to menti.com and you enter that code 562036. It's right there at the bottom of your screen, and you'll be able to ask any questions that you want, and I'm looking forward to answering them when we get to the end here in a little bit. So what I'm going to do is I'm just going to jump here and grab the results, and we're going to see what this part would look like in its optimized shape. So this is what that part would look like. You can see we tremendously reduced the mass on this part. Don't quite remember what it was. I think it was something like 3 point some odd kilograms. We've reduced it now down to a quarter of a kilogram. Maybe a little bit ambitious, so what I'm going to do is I'm going to use my Shape Explorer here that comes up when I'm done with the result. I'm going to beef that up just a little bit there so I get some nice robust members. These members here are what we defined with this minimum thickness constraint. That's how small any of these can get, and they got a little bit smaller than I'd prefer. So by just moving this slider, I can beef them up a little bit. But now I can see now I'm at somewhere around 0.35 kilograms. That's a part that I'm pretty happy with. But how do I know? How do I know that this is good? Well, all I have to do here is come here and click Analyze. What this is going to do now is it's going to take my part configuration as it is, and it's going to now run an analysis. So just like we ran the analysis initially, it's going to take those loads, take those constraints, and it will run a quick analysis on this. This should only take just a couple of minutes here, and then I'll be able to see the results of this exact part in its exact configuration. While it's doing that, something I might mention, what a lot of people notice, one of the first things they notice, is that it seems to have completely abandoned these two constraints here. And it's done that because this part was run with a minimized mass optimization. And the minimized mass, its goal is to limit stress or minimize the mass with a stress constraint on it. And what it determined was by putting material connecting here, that material utilization was doing nothing or doing very minimal to reduce the stress in the part, so it decided that it wasn't necessary. Had I run this as a maximized stiffness, it absolutely would have grabbed onto these, because to make the part as stiff as possible, it's going to grab onto everything and anything it can possibly grab onto to make the part as stiff as possible. And what a lot of people will do is they'll run both. You'll see that you'll get a similar shape, but slightly different with the minimized or maximized stiffness. And I can't stress this enough, there is no software out there that will or should be doing the design process for you. This is a tool, just like any other engineering tool you use, to help you better understand information about your part and help you come up with a better, more robust design. But don't let anyone sell you on the idea of a software doing the design for you. What many engineers will do is take the information from this, take the information from the maximized stiffness analysis, combine them together, and engineer a part from that. But to see whether it is surviving my stress, my analysis is done. I just can come here. I can come to my von Mises stress. You can see there is a bit more stress on here. In fact, there's some relatively high regions of stress, but those are because of the sharp angles here. I left those in because I want my design space to be as kind of blunt as possible, as blocky as possible. I know that when I'm actually doing my part design, a simple fillet put along this corner is going to take care of those. But most importantly, if I come here and take a look at my factor of safety, my factor of safety has reduced. Still, a large portion of the part is at 6, but as I come down here, as I get further and further down, you can see right when I get to about 2 times factor of safety, everything disappears. So I've got my 2 times factor of safety, but my part is now optimally designed. I have significantly reduced the overall mass of the part, but still maintain the safety factors that I need. And I can look at both of my designs here, and you see everything goes away at that critical 1.5 times factor of safety that I asked for. So my lateral loading is a bit more stressful on this design, but even with that, I'm getting the stress limitations that I specify. So ultimately, I now have reduced the mass of my part significantly. I've made the part lighter. I've probably made the part cheaper because I'm not wasting a bunch of material. I've made the part greener because I'm no longer utilizing that amount of material that I was using before. And I've made the part better for my vehicle because in this case, in this aircraft, I'm now only lugging around 0.35 kilograms for every single door hinge bracket as opposed to over 3. So I will either get better fuel economy on my aircraft, or it will allow me to put more passengers or cargo, which do pay to fly. Aluminum doesn't pay to fly. So I'm going to get better performance out of my aircraft as a result of this. If you think of it in terms of a super mileage vehicle, or any vehicle for that matter, the lighter weight you can make things, the more mileage you're going to get out of it, the better the fuel economy, the better the energy efficiency. But, and I can't stress this enough, it is intelligently designed driven by simulation, so that I meet my requirements, I meet my stress requirements, but minimize the amount of material that I'm going to use. Now, where do I go from here? What I can do is I can click this Fit Polynerbs. What it will do is it will wrap geometry around this part. So it will create a solid from this. Now I can come and export that solid. So come here to Save As, and I can bring that into a CAD system, and I can manipulate this and modify it, smooth it up, clean it up within my CAD system to come up with a design part, or within Inspire itself here. I need to wait for this to finalize, so that'll take just a second. There we go. Within my design here, I can also create some very clean geometry using Polynerbs. So not do the automatic, but what we do what we call wrap, where what it does is it analyzes the cross section of the part, and I can create these nice tubular features, and I can connect them together by bridging them. So I can say bridge this surface to this surface, and it bridges them together, and I'd go through and do that to the entire part, and I would actually end up with a part that looks very similar to this. Open, don't save, desktop. Give me just a second here to open this up. And where's it at? I think it's in here. Nope. Sorry. Please forgive me. I don't know. It's in here somewhere. Yeah. Oh, you know what? I bet you I can find it better in there. This is the one I want. There we go. I can end up with a very nice, smooth part that looks like this. Last but not least, just in the couple of minutes I have remaining here, I also have the capacity to do motion analysis within Inspire. What motion analysis allows me to do is simulate a dynamic system, a kinematic system, like with this this wing here. What this does is I come to motion. I come to my results here. It will animate this motion, the motion that I specify, and allow me to see the stresses inside my part as a result of a motion analysis. So not only can I test the dynamics of a system, make sure that all of my parts are interacting properly and I'm getting the motion that I want. The values that are automatically calculated as a result of that motion are then able to feed into an analysis or an optimization automatically without ever knowing what the forces are. I can do analysis or optimization directly from that. If you're interested, we do have classes on that, as well as some saved videos on a class that I taught last fall. Please do contact us, and we'd love to help you out. You can get the software at altairuniversity.com. And if you do need any assistance, you can always contact me. My email is eric, E-R-I-K, at altair.com, and I'd love to help you out. But that pretty much wraps it up for the demonstration. I hope you got something out of this. Hopefully, you've taken this hour and 15 minutes or so and gone onto that menti.com site, entered in the access code, and put your questions in there. Yep, I see it has just popped up again. So if you've had any last-minute questions that have popped into your head, or anything that occurs over the next, we've got a good half an hour here that we're going to tackle your questions. Please continue to go on to menti.com, enter that code in there, and I'd love to answer your questions. But I'll send it back to Norm right now to kind of wrap things up and open up our question and answer session. Thank you for your time, and look forward to answering your questions. So back to you, Norm.
Thank you.
Norman.
Thank you so much, Eric. That was a great presentation. I really enjoyed listening to you, and I hope our watchers and followers online have been enjoying it too. There's been a lot of questions coming in, and as Eric just said, please keep the questions coming. Go to menti.com. You can at any time enter more questions, or also give a thumbs up to the questions that have already been asked if you are wondering the same. So we will be asking the relevant questions. Eric, thank you so much. And let me start with the first question that goes on the of everything before we even talk about the software product. But one question that came in is, do I need a powerful computer to run the software that you have just been talking about?
Excellent question. So one of the great things about Inspire is it is very, very efficient in its utilization of computer power and graphics capabilities. So while I will say that the higher the power of the computer you have, the more memory you have, the better processor, the quicker and faster Inspire will run, it is very, very friendly with just about all levels of computer software. So assuming your software or your hardware can run Windows 10, that's usually enough to make sure that you'll be able to efficiently run Inspire. I have even installed it with a customer on one of those Microsoft Surface semi-tablet, semi-computer, and it ran perfectly fine. Again, the faster the computer you have, the more power you have, the more RAM you have, the faster the software will run. But we are very, very efficient with our utilization of hardware, so don't worry about the level of computer you have. It will run on there.
That's good to know. I mean, obviously, the whole lightweighting debate and being energy efficient and saving energy through lightweighting starts with the choice of your materials. And we have one question here coming in asking, is Altair Inspire able to generate composite material and run an analysis on it?
Fantastic question. I'm sure all of the questions are fantastic, so you hear me say that a lot, but that's a really, really good question. And unfortunately, at this particular moment in time, we do not have the ability to directly support a composite material. The limitations are the material has to be isotropic and it has to be homogeneous, which in the case of a composite directly using the ply layup does not apply to both of those restrictions. But that is not to say that we can't do an analysis on a part that is going to be Many of the competitive design teams that I've worked with using composites, they're using the information that comes from Inspire to then build up their composite from that. Essentially, what I tell them to do is homogenize composite material. So take all of the plies, kind of homogenize them together, come up with an overall strength profile of the composite material. Utilize that, and you'll be able to analyze it and then go back to your composite. So while we can't analyze the composite material directly, you can absolutely run analyses and optimizations on part that will use composite material.
Okay, thank you, Eric. And we have a great mix of questions coming in here today, touching also on the opening that you made, talking about the sponsorship and partnership for the Shell Eco Marathon. And one of the teams asked, "Is the software free, and how do we get it?"
Absolutely. So Altair is a huge supporter not only of the competitive design programs like Shell Eco Marathon and others that are out there, but we are a supporter of education in general. And we want to make sure that students are coming out of university able to do these high-end analyses because they're going to be asked to do it in their jobs. So we have a student version of Inspire. It is actually a fully functional version of Inspire, and it is absolutely free. You can get that at altairuniversity.com. But if you are on a team, if you are on a team like Shell Eco Marathon, you can also go to altairuniversity.com and get a team sponsorship. And the advantage of the team sponsorship over the student version is then you get not only a corporate level license, which will allow you to use Inspire as well as all of our other products in our suite of tools, but more importantly, it's going to give you access to people like myself and other application engineers we have that can provide you support, that can provide you mentoring. I travel out and visit teams all the time to provide training to them. So the sponsorship is absolutely free. It's a very quick and easy page. It takes you 5 minutes to apply for the sponsorship. I say apply, we're going to give it to you no matter what. It's just our way of then making that contact with you, and you will get the software for free, and we will provide you as many licenses of the software as necessary to make sure all the people on your team that are looking to do it, to use the software, are able to do it on their own machines. So you've got two different paths there to get the software for free. If you're on a team, I'd recommend going the team sponsorship, but it will cost you not a dime.
Thank you. That's great to hear. And somebody is asking here about the workflow and the work scheduling, saying, "I have an existing part I would like to improve. Should I first run an analysis, or should I start with the optimization?"
Great question. It's not absolutely 100% necessary to run an analysis first. A lot of cases, that's the way people will go because they want to understand the behavior, the design that they have right now. But if you know you're looking to optimize your part, you don't have to run an analysis, a benchmark, a baseline analysis first. You can hop directly into the optimization. There is no requirement for it. Like I said, a lot of people will run that initially just so they kind of get the idea where they are, but that is not a requirement. Don't hesitate to hop directly into the optimization. Just make sure that if you've got a design, don't optimize the exact design you have. Convert it into that nice big blocky design space that we showed in the demonstration, and then you're going to get the best optimized design possible.
Okay, and then I think the next question is somewhat also about optimization of your efforts. But the question is there any need to design, I think, something first, if we can just give the software a big block and optimize to what we need?
I've seen that done. And it's a tough question to answer in that case because it really is dependent upon that specific design or that specific use case. But essentially, what you want to do is you want to provide your hard points, your non-negotiables, the points that have to be there. Usually, the mounting and the loading, and you're going to differentiate those with the or separate those with with the partitioning, but then just fill up the entire design space you have. So one of the things that you have to mention, or that has to be there, and what I'd like to do is just kind of flip back to my my software real quick here, so I can kind of show you that. I'm going to open this back up. So you'll see here, even when I went and did the pulled this out and made a big block of it, I didn't touch this nose here because I know that my hinge is going to mount and it's going to go in kind of a U around here. So I need to make sure that I don't have design space material here. And then as this rotates around, it could interfere in this area here. So I'm not going to add material there. So what you do is you create an intelligent design space that does require a little bit of engineering, because you need to make sure that you don't have material where it would interfere with other things in your design. So while we aren't just going to give it a big cube and say go to town, we're going to engineer that cube, we're going to cut out that cube, we're going to make sure that it doesn't interfere, it does not exceed the design volume that you have. But for the most part, yes, after that, it can just be a big block that has your hard points on it, your locations that are not critical, and make sure you don't have material where it's not necessary or where it's going to be a problem. So, great.
I guess that's the reality where reality kicks in. I mean, the designs need to allow for some functions, and that function needs to be ensured. That is the reality of most applications. Another question pertains to the application of loads. When applying loads, how do we know if the figures applied are correctly? This is especially difficult for dynamic load cases. Again,
yes, and that's a really good question. In a lot of cases, we are making an educated guess with loads. And also, if you are not 100% certain of your loads, but at least you're certain of where the loads are going to occur and their kind of general direction, if you think about types of optimization you have, maximize stiffness and the minimize mass. Minimize mass obviously requires a very accurate load because it's stress-based, but maximize stiffness isn't. Maximize stiffness is going to create the stiffest part possible based on the orientation of the load, but no matter what the load is, that stiff part is going to be the same. So in a lot of cases, when people don't have the accurate values of the loads yet, they'll run a maximized stiffness, just making sure they orient it possible. The other thing that you can do, especially in a dynamic scenario, is if you incorporate a motion analysis into it. Since the motion analysis will be calculating the loads and the reaction forces at all of the joints and all of the contact areas, it'll do the job of calculating the loads for you, and you don't even have to know what they are. It will allow you to essentially run a dynamic optimization by calculating the loads and then optimizing it, taking into account each one of the progressive steps as it moves through that motion analysis. That's what you saw in that flap and spoiler. I don't know what the loads are on there. I didn't put them on there. It calculated them. So that's another route to go as well.
And the following question closely related to that is, why is the optimization in general based on stiffness and frequency as its constraints?
So we have to come up with some sort of goal, and two of the most important, or three of the most important things that the goals that we set are stiffness. We want the part to be as rigid as possible, as non-flexible as possible. When you think about this aircraft door hinge, if this part were not rigid, if it were allowed to flex, as you opened that door, the door to the aircraft could become misaligned. It's going to pull, it's going to flex that part, and closing the aircraft door would become difficult, if not potentially impossible. So stiffness is a key factor. Another key factor would be stress, and that's in the case of that door hinge bracket. You could kind of go either way, or like I said, do both, a happy medium between them. But stress is an important factor when we want our part isn't going to break. So you got some sort of suspension part on there, which not only has to be stiff, but has to be resistant to stress. When it comes to frequency, frequency is a critical factor because we want to make sure that our frequencies are not or our parts are not resonating at a frequency that it's going to see in design. If you've ever sat on an aircraft, you listen to the buzz of the engines. If you ever put your head against the frame of the aircraft, you can feel the high frequency vibrations. If we had an engine mounting part that vibrated at that frequency, well, we've probably all seen in our engineering education, all seen the videos of the Verrazano Narrow Bridge crumbling to the ground. That's the sort of thing that we'd see on a bracket that vibrated at the frequency that the engine was putting out. So.
Hey. I would like to remind you all, please keep the questions coming in. It is not too late yet. We still have a bit of time. If you have any burning questions, go to menti.com, enter the number shown on the screen and in the chat, and please ask your questions. And in the meantime, Eric, I would like to ask you, how is Inspire different from other Altair software products like HyperWorks and HyperMesh?
Great question. Glad to see there's some people familiar with some of the other products that we have. So it's not actually. It's not, and it is. So I'll go with that. I know that sounds like an odd question, but I promise we'll get around, or odd answer, but we'll get around to the end here. It's not different in the fact that it's actually using HyperMesh in the background. So we're taking advantage of the power of Hyper. The difference is Inspire is instantly easy to use. It was designed to be very user-friendly, very CAD-like, and very easy to use. So we can consider it a very easy to use, very user-friendly geometry front end on top of HyperMesh. So for an analysis setup standpoint, it's using HyperMesh. For a meshing, it's using SimLab, and then for the analysis is using OptiStruct. So it's a front end for all of those softwares that's very easy to use.
Okay. No, thank you. And can you also elaborate a bit, for instance, towards SimSolid, SimLab, and Solid Thinking?
Sure. Yeah, absolutely. So SimLab is it's a meshing tool. It's used to mesh parts. Its true power is in tetrahedral meshing, so little triangular pyramids. And the real power of SimLab is the fact that it is capable of doing an analysis of the geometry. It takes a look at the geometry. It's what we call feature-based meshing. So it creates an intelligent mesh based upon the shape of the part, making sure that we get an accurate mesh, because an accurate mesh is accurate result. And then it utilizes HyperMesh to set up the analysis parameters and OptiStruct to run it. Solid Thinking is actually a brand name for a number of our tools. We're actually kind of moving towards bringing everything under the Altair umbrella, so to speak. So Solid Thinking is a generic for a number of our tools, but these that fall under the Solid Thinking would be Inspire Casting, Molding, Inspire Studio. But all of them are Altair products, with SimLab being a meshing tool, HyperMesh being a mesher, a preprocessor, yep. OptiStruct being a solver.
Good. And while we are on differences, maybe you can also say a few words. We got a couple of questions on that topic. What makes Altair different from other CAD softwares that would be available in the market?
Excellent question. So I know there is a tremendous draw in some of the CAD softwares to just say, okay, well, I've used this to to create my geometry. Why not just continue on with the analysis? And then that isn't what the problem then becomes. Altair's been in the analysis game since the beginning. We started out with HyperMesh and then ultimately OptiStruct and Radios and all of our other products. We've been doing this for 30 years now. We know the game. We know our software. We know analysis, and we can guarantee that utilizing our software, when you set your analysis up correctly, and you will be able to do it correctly and easily within Inspire, you're going to get correct results. Some of the CAD softwares that have decided to get into the FE game, they're kind of newcomers in it. They went out and they bought codes. They didn't develop them themselves. They don't have that history in it. For simple kind of educational theoretical ideas, cantilever beams bending, stuff like that, they get good answers. But once you get into anything even remotely complex or real world, in a lot of cases, you can't even set it up properly, and you're going to get results that drastically differ from reality. So, like I said, we want to partner with the CAD packages, use them for the geometry creation, and then set it on up in Inspire and get the correct answers.
Thank you. Thanks. And again, reminder: we are having 2 or 3 questions left for Eric. If you have any other urgent questions, please send them right now, and we'll be able to get through them before we close the presentation today. But before we do that, there is some interest here, Eric. Where can people get the lessons about the wing material, like the one you showed at the end of the presentation?
So the wing that I did was I did that myself. I'd be happy to share it with anybody that wants it. Like I said, my email's eric@altair.com. Just make sure you spell it with a K, a good Swedish spelling there, ERIK@altair.com. I'd be happy to share it with you. But on altairuniversity.com, we've got a number of educational tools on there. We've got videos, we've got training, so you'll be able to learn to do things similar to that that wing, where you'll see some of the other motion capabilities. So that's going to kind of be your primary resource for getting stuff online. But never hesitate to get in touch with me. I'm happy to do any material or assistance I possibly can.
Thank you. And there is a lot of information. There's a lot of interest in the sponsorship application. A team is asking here very specifically for the faculty information. Do the students have to fill in the name of their team leader, as in their Shell Eco Marathon team leader, or their team lecturer?
It's so in the case of the faculty advisor, what we just want to do is we just want to know which faculty person is advising the team, is kind of responsible from a faculty standpoint, who that is. If you've got multiple, it doesn't matter which one you pick. It just needs to be somebody on the faculty that's responsible for the team. Every team is going to have some sort of faculty advisor, so just that person. Just the person there, somebody who's not a student but a faculty member.
Okay. We're getting back to some more technical questions, and we've been talking about the isotropic and different materials earlier. Here's a question about does the software optimize non-linear materials?
No, it does have to be a linear material. It is a linear static analysis. So again, you'd need to homogenize it. You need to kind of linearize. I'm going to make up a word there. Linearize the material. So come up with a linear equivalent to that material, and then ultimately, what you can do is come up with a design, and then you can test that in a nonlinear analysis tool. OptiStruct does handle nonlinear analyses, but you'd have to set it up through HyperMesh. Inspire provides a subset of the full capabilities of OptiStruct. So.
Yeah, and does Altair Inspire allow you to simulate the required torque for fastness?
So the required torque for fasteners, no, we can't tell you what the torque needs to be. But if you do have a preload number, we can simulate the preload, but we can't tell you what that ultimately needs to be. No.
And can we use Altair Inspire for dynamic simulation? And if you can show us the steps.
So dynamic simulation, the only way that we could do dynamic simulation, and let me come back to my screen here, my software screen. I'm going to just open up the flap and spoiler because that one, like I said, has the results on there. So what I did first in this case was to run a motion analysis. You'll see I've got all of the things jointed up here. So any interaction between all of the different members here, these joints were automatically created in Inspire, just like the fasteners. And then I put a couple of actuators in here. They're actually hidden behind this this spoiler here. This actuator, which is going to raise the spoiler, and then there's a couple of motors which are hidden, and that motor turns this pin right here, which utilizing all of these drops that flap. And so the dynamic analysis is I run the motion, and once the motion is run, it's going to actually calculate all of the forces at all of these joints. I can't show them to you because since I ran the analysis, those are now incorporated into there. But if I ran just the motion, I could click on that joint and it would tell me what the forces are. And then it takes those forces, and when I run the analysis, you'll see motion analysis doesn't run. But if I were to select that, it would say, do you want all of the different steps that it went through? So every step of the motion analysis, it would run an individual linear analysis. So you create a dynamic analysis by essentially stringing together all of the different individual steps in the motion analysis. So that's our way of doing a dynamic analysis. It has to be motion driven within Inspire that then can be run, sent to an analysis. So.
Thanks. More about the learning tools. Where can the participants and the students listening here get the series or chapter videos for Altair? So I'm saying for this presentation, the recording will be available on YouTube. But I guess the question also pertains to other learning materials on Altair. Maybe you can say something about that as well, Eric.
Yeah, absolutely. So your central point for that is absolutely going to be altairuniversity.com. We have a large number of materials in there as well. We've recently posted two 2-hour-long videos. So in the fall, we always have what we call our educational webinar series. So Inspire is always there. Inspire Motion is always there, and then we usually have 5 or 6 different other tools. We do a 2-part series, 2 hours each, for our different tools. That happens every fall. We ordered those. I'll figure out a way to make sure we get that information distributed out there. But I'll tell you, the best way to get educational materials is to go to Altair University. You get that sponsorship. You get on our mailing list. We can contact you directly. You will absolutely get an invite to our exclusive educational webinar series every fall. And you can contact us that way and through our support, because you will get assigned somebody who can handle support. We can get you all the educational materials you want, including the class files with all of the exercises and any videos you want.
Thanks, Eric. Are there any other types of Altair Inspire? I suppose this relates to other versions?
So with Altair Inspire, it's our structural and optimization in motion. We have another tool called Virtual Wind Tunnel, designed based upon the interface that Inspire utilizes, that allows you to virtualize the generation of a wind tunnel. So it's a little bit more complex than Inspire, because you have to have a mesh generated for your vehicle or wing or whatever you want to slap in the wind tunnel. But we have some, in fact, there's a recording of the virtual wind tunnel that was done for our educational webinar series. But it'll walk you through how to generate that mesh in HyperMesh, bring that in, and then once you've got that mesh in there, it's as easy to use as Inspire. It's a graphical way of generating the overall size of the wind tunnel and then the flow through it, and you can do a wind tunnel analysis. We've got another tool, Inspire Studio, which is kind of a industrial design CAD type tool, and then some of our manufacturing, casting, stamping, extruding, that they're based on the Inspire interface as well. We're actually moving all of our softwares to the Inspire interface because it's so easy to use.
Yeah. Is it actually possible to make animations in Inspire, or would students need another software to support that?
Yeah, so you can, when you're animating it, if I can actually pop back here to my screen here, when I go to my results here, oops, you'll see I can start the animation. And right next to this right here, I've got this little record button. So if I click that, it will record that animation into, I believe, an AVI or a GIF file. Or you can use, I'm a big fan of Snagit. I use that to capture things. But yes, we have the capacity to record an animation directly within Inspire by using this little button. I suppose it probably should be red, be a record button, but that's our record button, and it will create the recording right there in Inspire. So great question.
Yeah. Another question has come in, and again, last time I'd like to remind you, if you have any other more burning questions, just get them in right now. We have 10 more minutes left to answer your questions. So if you want to ask Eric any question to the software that you've just seen, please enter it now into menti.com and I'll be able to ask it. In the meantime, somebody has been asking, I have a part in the format IPT, as in from Inventor. Is it possible to optimize the design of this part using Altair Inspire?
It's a good question. Let me just check here. We don't need to switch over to the thing. Let me just, or we can. Let me see if that's one of our supported formats. Yeah, right there. So if we're showing my screen here, yeah, Inventor IPT. So we can bring in the native IPT file directly in there, or if you want to convert it to like an IGES, a step, or a Parasolid. But we do support Inventor IPT files natively. So, yep.
Okay. And another question, I think we've answered it before, but I wanted to double check. Can we use Altair Inspire for dynamic simulation? And if so, can you show us the steps?
Yeah, that was one we had tackled, but just to reiterate on it, the steps would be run it through motion and then feed an analysis from the motion. Yep.
Okay, good. Is Altair Inspire actually used by big companies, is somebody asking?
Oh, absolutely. Yes. There are, it was originally designed for kind of designers and people who weren't familiar with finite element analysis, but because it's so amazingly easy to use and so quick to use, even people who are fully capable of running a traditionally full level finite element analysis are embracing it and using it. And as a result of that, there's a large number of our customers in automotive, in aerospace, Boeing, Airbus, SpaceX, just thinking of companies I've trained directly, Ford, Chrysler, Honda, GE Aviation. Yes, there are many, many corporations, a large number of them. Even Harley Davidson motorcycle is using it to optimize as well. So yes, many corporations are utilizing this exact software.
Thank you. Thank you so much. There is actually a last question that I've seen, and I'm able to answer that for a change. Is it possible to share the recording of the session? Yes, the recording of this session will be available, and you will receive the link to YouTube to rewatch it. And of course, please don't hesitate to share it with your peers, your colleagues, your friends at university, anybody in your team or even beyond your team who might be interested in learning about using Altair Inspire. That being said, Eric, I would really like to thank you so much for giving us your time today, for giving us this great presentation and answering all these questions to our audience. It was truly and interesting. So big thank you from all of us at Shell Eco Marathon, and thanks to the students for turning and taking part. There are more virtual learning sessions coming up in May. Tomorrow, we'll be hearing from Eric, for instance, about fast meshless analysis. So if you haven't registered for this webcast already, please do so through our website, and we'd love to have you join again. Otherwise, thank you so much. Stay safe, and goodbye.